Hey, what's up everybody? It's Mr. Boylan and we're going to continue our discussion on acids and bases. As you take a look at the content objective, again, we're going to talk about how chemical equilibrium can be used to describe the proton transfer reactions of acid-base chemistry. Specifically in this video, we're going to look to identify strong acids and bases, define the strength of strong or weak acids and bases as they relate to the equilibrium constant K. So we're really going to start tying in some of the information from the equilibrium unit. And then lastly, we're going to calculate percent ionization of a weak acid or base. Okay, so when we are talking about the strength of acids or bases, it's a measure of essentially the size of the equilibrium constant K when it reacts with water. And whether or not it reacts comes down to really two things. What is the polarity and the strength of the bond that we're talking about? Okay, now when we're talking about acids, the equilibrium constant is called the acid ionization constant, or Ka. And recognize that Ka is just another equilibrium constant. It's still relating the concentration of the product to the concentration of the reactants. And the larger that Ka value, the stronger the acid is. Okay, now let's think about what this means as we relate a general equation for an acid in both the forward and the reverse directions. I'm going to take a little bit of liberty here and recognize that our acid molecule is made up of a hydrogen ion and some other anion, and we're going to react it with water. Now, in the forward direction, our acid molecule is going to be donating that proton or donating that hydrogen ion, and water is going to be picking it up. In the reverse reaction, the hydronium ion is going to be redonating back to the anion that originated from that original acid molecule. But let's think about what the ionization constant K means. Remember, it's the ratio of the concentration of the products to the concentration of your reactants. And if we're talking about a strong acid, we're talking about the forward direction being heavily favored. In other words, what's going to happen in this reaction is the acid molecules are going to completely ionize into the hydronium ion and that anion from the original acid molecule. There's going to be very little of the original acid molecule present at equilibrium. And so as you think about at the sort of particulate level what's going on in solution, yes, equilibrium indicates a sort of dynamic back and forth, but with a strong acid, we're going to have complete ionization, and the majority of what you're going to find in solution are going to be those hydronium or hydrogen ions and the anion from that acid molecule. So because we have in strong acids or bases complete ionization, our equilibrium position is going to be very, very far to the right, lots and lots of products. And so we're going to have very large Ka values, lots of products, very little reactants. They're also very strong electrolytes because we have all these charged particles in solution. And in fact, many times we don't even use the equilibrium arrow. We just use a single arrow indicating that the reverse reaction isn't even going to play a role here. So your equilibrium constant values for strong acids, very, very large. Okay, so as you think about strong acids and this general equation to represent a strong acid, again, we're going to assume essentially complete ionization. So this is going to be negligible to non-existent. We're going to have complete ionization. We're going to have mostly products at equilibrium. Therefore, our equilibrium constant for acids, or acid ionization constant, is going to be greater than 1. An important thing to keep in mind when we are talking about strong acids and bases is that you need to recognize that the concentration of the hydronium ion when we're talking about acids, or hydroxide ions when we're talking about bases, is equal to the original concentration of the acid or base, respectively. Now, we're going to take a look at a sample acid here, but because we're talking about a strong acid, we're really only focused on the forward direction for this reaction. And again, what that means is at equilibrium, we're pretty much only going to have these things in solution. And so as we look at sort of the particulate diagram, you can sort of imagine each of these hydrogen ions hooking up with one of these anions to form the original acid molecule. And so as you look, this would partner up, this would partner up, this would partner up, this would partner up, and this would partner up, and these would partner up. And so however many original HA molecules you walked in with, it's going to be the same number of H ions that will be in solution. So whatever your concentration of the acid molecule is to start with, it's going to be the same as the concentration of your hydronium ions once you've reached equilibrium. And this is true of any strong acid or strong base because we have complete dissociation. That 1-to-1 stoichiometry ratio is all we need to recognize and understand. Okay, now an important thing to watch out for, though, is for those strong bases that include metals from group 2. For example, calcium hydroxide and all the other strong bases that form from metals in group 2 are always going to have 2 hydroxide ions for every 1 formula unit of the compound. What that means is that your stoichiometry isn't going to be 1-to-1, but 1-to-2. And the example that you're given is, well, if I have a 0.1 molar calcium hydroxide solution, the concentration of the hydroxide ions is going to be twice that, just based on the ratio of the ions in the formula. Now, it's really, really, really important that you commit the strong acids and strong bases to memory. I provided you with a mnemonic device that I use to help remember which the strong acids are. He could have been her ideal newfound superhero. Hydrochloric, hydrobromic, hydroiodic, nitric, sulfuric, perchloric are your strong acids. It's really important that you commit these things to memory. Recognize that the strong bases then are any of your group 1 or group 2 metal hydroxides. Commit those to memory. You will really struggle on the test if you do not. Okay, and the last thing to sort of keep in mind here when we talk about strong acids and bases are your oxyacids. So when they're not binary acids, you'll often be asked to determine, which acid is the stronger oxyacid within that group. And it comes down to the idea that the oxygen atoms are very, very electronegative and do a really good job of pulling electrons away from the site where the hydrogen ion is bonded. Essentially polarize that bond more and make it a little easier to remove that electron, therefore making it a stronger acid. Now, as you take a look at your notes or at the example we've got on your screen here, we've got a series of oxyacids all pertaining to the same group. So hypochlorous, chlorous, chloric, perchloric. As you look at each of the subsequent oxyacids, we've got a greater number of oxygens. And because those oxygens are very electronegative, they're pulling the electrons away a little more strongly in this bond where we have the hydrogen ion, making it more and more polar. So the bond here is more polar than the bond here, than the bond here, than the bond here, because we have more oxygen sort of pulling it away, which makes this the strongest of the acids in this oxyacid group. So the more oxygens there are, the stronger that acid will be because of the greater polarized bond. Okay, and that brings us to weak acids and bases. If a strong acid is something that's completely ionized in solution, a weak acid is not completely ionized in solution. Generally, we're talking about less than 10% ionization. Here, our equilibrium position is going to be far to the left. We're going to have a lot of non-ionized or original reactants left in solution when we reach equilibrium, indicated by small equilibrium constant values. They're going to be weak electrolytes because we don't have a lot of those ions in solution. And keep in mind that the vast majority of acids and bases are weak. You don't have to memorize a list of those. Just recognize that if it's not one of the strong ones, assume that it's a weak acid or base. All right, so now as we take a look at a couple of reactions for weak acid or weak base, respectively, think about what this means in terms of your equilibrium constant. For your Ka expression, again, for a weak acid, we're not going to have a lot of the forward reaction. We're going to have a lot of the original acid molecule, which means your equilibrium constant is going to be very small, less than 1. We can apply the same idea to weak bases. Recognize we use Kb here for our bases instead of Ka, but the idea is the same. We're not going to have a lot of this ionization that happens, or dissociation. We're going to have a lot of our original base molecules left in solution. So once again, our equilibrium constant value is going to be much less than 1. So let's take a look at, again, that generalized acid reaction with water. Let's look at both the forward and reverse reactions. Again, in the forward reaction, we'll have that ionization of the acid molecule. In the reverse reaction, we've got the reformation of the original acid molecule. Our equilibrium constant expression for a weak acid, again, we're not going to have a whole lot of the forward reaction. We're going to have a lot more of the reverse reaction, which means we have a lot of our original acid molecule in solution. At the particulate level, notice a lot of our unionized acid molecules are in solution, very little of the ionized form. But here's really where we get to the idea of equilibrium and recognize that we can't just use stoich ratios like we did with the strong acids and strong bases, because all of this hasn't reacted, hasn't ionized to form our products. Only a little bit of it has. And so as you think again about what's happening here, you've got the forward reaction where you've got this ionization, the reverse reaction, we have the reformation of the original acid molecule. In a weak acid, we've got the reverse reaction is favored. And so we've got a lot of this HA that's still left. And so we can't, again, assume that this concentration is going to be the same as the original concentration of the acid molecule, because not all of it has dissociated. And here's we get to the wonderful world of ice tables coming back. Okay, so when we're talking about weak acids or weak bases, you're going to have to use an ice table then to figure out what this concentration is going to be, because we're not going to have ionized this acid molecule completely, so we can't just use the stoichiometry. So as you look at this example ice table that you have in your notes, if we have, for example, an initial concentration of our acid of 0.1 molar, that means the initial concentrations of our hydronium ion and that conjugate base, or the anion from the original acid, is about 0. You'll set up your changes in those concentrations. And then you'd end up with these equilibrium concentrations, which you would then plug into your equilibrium constant expression and solve, which could be kind of difficult, especially when we get the quadratic equation involved. Okay, now, lucky for us, because weak acids and bases really don't ionize very much, the change in the concentration isn't going to be very large. In fact, many times it's going to be small enough that we can neglect that change in concentration, which will make solving these problems a lot easier, as you'll see when we work through a couple of examples. And as you take a look at your notes then, that simplifies your equilibrium constant expression from what you see here to what you see here. Again, that just eliminates the quadratic, makes your life really easy. And with enough practice, you can even get to the point where you avoid having to even do these ice tables, but we'll practice initially with them to help you better understand where these numbers are coming from. Okay, and then the last thing you'll be asked often is to determine what is the percent ionization of that weak acid or base. How much of the original molecule has ionized? But it's a very quick calculation once you've determined the concentration of your hydronium or your hydroxide ion if you're dealing with a base, and just compare that to the original concentration of the acid or base to figure out what the percent ionization is.